Hello, welcome to CM Videos, a YouTube channel where we try to help you get started with modeling. The object of this video is on failure envelopes. Failure envelopes are very important for numerical work, especially people that are looking at predicting damage of materials. So understanding the failure envelopes, it's really important. And so this video is aimed at helping you find a way to generate failure envelope from your simulations. And the outline that we're going to work with as we try to do this, first I want to talk about combined loading and introduction, because this is really important for generating failure envelopes. And then we'll look on to how to implement this combined loading within ABAQUS, leading us to the idea of generating a failure envelope. And then finally, how to extract stress strain data and the point from the stress strain data that will drive you towards getting the failure envelope. So that's the object of this video. If this is the kind of content that you like, please do subscribe to this channel and click the bell button so that when contents like this are made, you'll be able to see it. So to solve this, to look at this, I want to introduce you to this student. Her name is Ella. She's a first year PhD student, and she's had a meeting, one of her meetings with her supervisor. The supervisor suggested that, I want you to generate a failure envelope from your numerical work. And like most supervisors will do, she went off to do this work, trying to figure out what the problem is. So, and the question she was dealing with is, how can I generate numerically a failure envelope from the simulations that I've been running on a composite material that I have? And she was pulling her head, wondering how this problem can be solved. So she decided, okay, to go and speak to Dan. And again, Dan is one of the postdoctoral researchers that are working within the team. And so Dan, being quite experienced, decided to give her a bit of an advice. He said, you should really use combined loading to try and solve this problem, because combined loading is really how you can generate failure envelopes. You need to look at the interaction of loads on the domain to create failure on the material, and that's what you're going to do. So Dan went on to explain that the kind of problem what you're trying to really do is think about your failure as a two-axis problem. So there is a horizontal axis, which is probably a stress axis, and there is a y-axis. So you have two stresses interacting at a point. And every time these two stresses interact, depending on their size, they will lead to a point, a failure. So this data is taken from the worldwide failure exercise. Yellow points are the points of failure, depending on the combination of an x-axis load. So what you see here is axis in the x, the loading in the x-axis, and the loading in the y-axis. So depending on the combination, you would have a certain kind of failure happening on the domain in that way. So, and the idea of your failure envelope is then to end up creating an envelope that captures this domain. When you sit within the failure envelope, failure hasn't happened. And anything outside that envelope means failure has happened. So you could see the importance of failure envelope in trying to predict something like damage and its evolution on any kind of material, like in this case, a composite material. So understanding this boundary in space through which this failure happens is absolutely important, again, for some student like Ella, who is trying to deal with this problem. And so this is what we're going to try and help her. So Dan is right in suggesting that this is what you need to do. And he's giving her the theory behind what Ella needs to do. But the problem is, how would she go about trying to generate these multiple points from her simulation to be able to then define this failure envelope numerically, especially if you're testing a domain, a material that doesn't have a failure envelope existing already for you to use. In this instance, the failure envelope we have here is for a composite material, a unidirectional composite material from the worldwide failure exercise. So, but what if you're testing a variant of that? So doing this and generating numerically the failure envelope would help you to understand these boundaries, and then you can use it within your simulation. So Dan's advice is correct, and this is what we are going to do. So the question, of course, that we're dealing with is, how can I generate such failure envelopes for a UD composite, like in this case? So what do we need to do? There are a few things that we need to be aware of. So this first quadrant in this failure envelope is a quadrant where you have the stress in tension in the x-axis direction interacting with the shear stress in an upward direction. Now there's also the second point where you've got the stress in compression. So what you have here is a stress in compression acting on this domain, mixing with the shear stress. So you need to be careful about those 2 points as you try to generate the failure envelope, distinguishing the point where you've got a positive stress and a negative stress in the uniaxial direction. So let's then begin to think about how to implement this numerically within the idea of this combined loading. So we start off with a representative volume element of this problem. So this is a typical UD composite, maybe with other asperities within it. And so what we're going to do with this case is we are going to hold one end, so apply one loading on one end, and also implement periodic boundary condition to this domain. You don't have to use periodic boundary condition, but it's really easy to work from a periodic boundary condition to generate your failure envelope. And already I've made some videos showing how the periodic boundary conditions are, so please do refer in the card for those videos to help you pick up how the periodic boundary condition will be implemented on a domain like this that we are using. So the first loading type we need to apply on this domain in order to create the failure envelope would be the X domain, the X-axis loading. So it will be some kind of displacement in the X-axis. This will be simulating uniaxial XX deformation. Now the other thing is a pure shear simulation. I prefer to use a pure shear rather than a simple shear for a reason in the video again that I put in the card, which I try to show you that pure shear is better for simulations than simple shear, especially if you are interested in failure envelopes in the way that we're looking at in this video. So how would we impose a pure shear simulation to the domain? Okay, what we need to do is to apply 2 stresses, 2 displacements at those 2 nodes as shown in the schematics. And when you combine this loading, a uniaxial plus a pure shear stress case, then you get a combined loading. And the behavior of this domain at this instance will lead you to generate a point on your stress strain data which will fit in within the expected failure envelope. So that's really the principle of what we are trying to do with this video in terms of generating failure envelope numerical. So to illustrate this, the first thing we're going to obviously have to do is to think about our case study. So I'm looking at again a UD composite, and this UD composite will have a virtual domain that looks like here, random distribution of fibers within the domain. The fibers would have a diameter of 20 microns. The dimensions of this system is about 100, 120. We'll look at that when we start the simulation. And then the next thing we need to think about here is the materials. So again, because I'm using a micromechanical approach with RVE modeling, so I need to find the properties of the fiber independent from the properties of the matrix, and hoping that from homogenization of the domain, then we could extract the values of the stress strain data. So my fiber will be A-glass with a fiber volume fraction of 5%, and the other properties also are there. Now, obviously, the loading type that we need to simulate would have to be, like we said, we want to do a case where you're looking at here. So this first block where you have a positive X and a positive Y. So that would look like this. You're looking at the domain where the system will look like that. So you're applying a positive loading in this direction to create this positive uniaxial X case. Obviously, this other one and that one there are the shear cases, so that's not a problem. Now, for the other side to it, when you're looking at the compressive direction, so if you go into this compressive side of the domain, now all of a sudden, in this case, you're looking at a negative uniaxial case. So that will be the second loading type that we'll be looking at. And how do we reflect that? So of course, we'll have to change the direction of action of the uniaxial load that simulates our uniaxial X deformation. So you mix those together, and then you generate a new set of simulation, which will help you populate the behavior in the compressive direction of this failure envelope. And then in the end, we'll bring everything together to hopefully create this stress strain, this failure envelope. But I've got to say that what you're looking at is you want to navigate all the way through this failure envelope. So there will be multiple simulations to be able to go all the way until you go around and come to the end of this failure envelope. So it's not just a single simulation. For this exercise, we'll just be doing only a single simulation to show what you need to do with this. So what we're going to do next is to jump into ABAQUS and then walk your way through the whole process and see what we're expecting to do. Again, if you're finding value in what I'm saying, please do click the like button so that this click the like button and put a comment in the comment section of what you think about this whole process, how you're using it. Okay, let's go into ABAQUS and begin. Okay, so welcome to ABAQUS. So what we're going to do with this is try to set up this combined loading that we spoke about and try and do that within ABAQUS. So the first thing I've got to say is that we're going to use a script to do this. So if I show you a bit of the script that we're going to use, so I've already written this pre-script to generate the domain of the unidirectional composite, but the actual implementation of showing how all that would happen, I will show that. So this is the script. Again, I'll put this script in the link, the description section of this video, so that you can download it and use as well if you do want to follow along with me. So I'll just copy the script and then go back to ABAQUS. So I'm going to run the script. So if we put it in here, so it will run through, generate the domain, walk through all the process and apply and generate the virtual domain. So this is our virtual domain that we're going to work with. So I'll just provide the properties of the material. So in this case it's fiber. So our fiber would have a Young's modulus of 73.9 and 0.2 for the Poisson ratio. The matrix is polypropylene, so it would have an elastic property of 1.308 and 0.4. But then we want it to fail plastically so that we can generate the failure envelope. So this will be 48.6 and 0.0. So these are the properties of the composites. Now we just have to assign it. So if I open this and then the section assignment, so if we double click on the matrix bit, so we're going to make that the matrix. So I'm going to select everything, press down shift or control and deselect the matrix, leaving the fiber only there. So we can then have the fiber and then we could change this to materials to make sure that the domain is exactly the way we want it. So I'm going to mesh this domain. It's recommended 2.9, so let's use 2.5, 3.9, so let's use 2.5. And then I'm going to use a triangular shape to mesh this domain, just because of the nature of it. So it makes sense to use a triangular shape to mesh the domain, but of course you could use any other element shape to mesh your domain. So we've got that. The important things that we need to do, so we need to create a corner node. So corner node, so this is a set of corner nodes because that's what we are going to use. So I'm going to pick up all the 4 corners of this domain. So we pick that up. So that formed the set of corner nodes. Then the other thing that we need to do is we need to create the history that we're going to use to analyze this. So but before we do that, we need to create a step. So double click on step. So I'm going to call this my loading step. Okay, so accept all the default. Then we now create the history. So I'm going to call this corner node history output. So the corner node history output will be related to the set of corner nodes that we've talked about before. So we're going to use the RF1, RF2 reaction forces in the X and Y direction, displacement in one, displacement in Y, and then the coordinate positions for X direction and coordinate position for the Y direction. Again, if you're unsure about this, please look at the video that I put in the card that explain how you can actually do this. It's a video titled How to Generate Stress Strain Data for a PBC enabled domain. So please look at that video. It will explain a little bit more to the thinking about this. So we have generated all that. Now with our boundary condition, okay, so in this case, I'm going to call this fixed N1. Okay, I'm fixing this in the N1 direction for node 1. So I'll select this corner node and I'm fixing in both X and Y direction according to the domain that we're working with, which is what we specified earlier on. So now we're going to create the uniaxial X deformation. So I'm going to call this uniaxial X loading. Okay, so that will be a point happening there. So at that bottom corner, I want to load it in the X direction. I'm going to put the value of 12 here because the domain we're working with is a 120 by 120 domain. So 10% X loading will be 12 in that direction. Now we'll do the same for the shear. So but we have to have two. So I'm going to call this shear in the XY direction, XY plane. So this will be in this case. So I'll pick that corner point and I'll try and use the same value as 12, but again, depending on the combination, you can keep changing this. So this will be acting in the Y direction, one of the pure shear components, and then the other second shear component. So this will be again shear in the X, the YZ, the YX direction. So this will be acting in the X direction, and it will be a value of 12. So we'll put that. So if you think about what we've got here, so we've got a case of this, which is pure shear, and a tensile pull on this domain here. And we've meshed the domain. We have everything that we need. So we just need to create the job. So this first job, I'm going to call it combined X positive XY, so which is the tensile condition. So we accept that. Now, what we're just going to do to create a compressive case is I'll just create a copy of this. So we could call it, okay, so we've got that in compression. So with that being in compression, so what do we do? So with the compression case, the only difference is the uniaxial X would have to change direction to a negative to allow for compressive loading. So that means at this point we're applying a compressive loading, and that's about all. So again, for this instant that we're looking at, so we can then look at the case again. So what I'm going to call this is combined XX negative XY with XY. So we've got two cases that we're interested in. So what I'm going to do with these two cases is to write input. So put the first one and write input the second case. And then we'll find where this is located. So set working directory. So I'll copy and Control C and Control X to cut. And then I'll find where they are in my computer. Okay, so I found where those two files are and I've harvested them. Then I've come into MATLAB. MATLAB is the next domain that we're going to use, because what we want to do is to apply periodic boundary condition on this domain. So now we're sitting in MATLAB. We need to deposit those two input files that we've created previously. So I'll paste that here. So basically I've got those two. Clearly, for us to be able to apply periodic boundary condition, we need to use PBCGenLite. Again, if you don't know about PBCGenLite, the video in the link that I put above in the card would explain to you what PBCGenLite is and how to apply periodic boundary condition on a domain. So this is what we're going to do. So there's a few videos on this channel where I've used PBCGenLite to show this. So please refer to them, but we're going to show how you can do it again within this domain. So PBCGenLite is basically a P-coded MATLAB file that will do this, and we have two cases that we want to run with. So now I'll type PBCGenLite here, so calling it, and then it'll ask me which of these am I looking for. So I'm interested in this, which is one of the cases. What PBCGenLite will do first, it will plot all the nodal points and especially the boundary nodes. Okay, so I'm going to copy this link, which is the updated link. Navigate to that location, then run the ABAQUS version of this. So while still in run ABAQUS job equals that new load interactive. So what this is doing is that it's now running this updated file, which has periodic boundary condition incorporated within it. So it's running this simulation so that at the end we're going to get a stress strain data, and we're going to get a simulation result for this first instance where we're applying a positive load in the uniaxial direction. So it's run through and it's completed that, and we're happy. So now what we're going to do is that we're going to navigate our way back up to still the main workbench of PBCGen. So we're going to call PBCGenLite again. Now we're going to run the second case, which is a negative case. So again, it will do the same, apply periodic boundary condition to this case, which is a negative case. So we copy that link. Now we call ABAQUS again, still, but we have to navigate to that environment where ABAQUS is, okay? So where this job is. So I'll put the new name and then interactive. So what this again is doing is that it's running within, it's calling ABAQUS within MATLAB, running the simulation, trying to generate the output database file, which we are going to plot subsequently to try and see if we can extract the values that we're interested in. So it runs through and it will go to the end, and at the end, okay, the job has been completed and we're happy. So what do we do? So we have basically two job files that represents this first instance of the simulation. Now we're going to then go back and look at those results. So I'll just look at the first instance. So I'll copy that link. So now I'll jump back into ABAQUS. So here we are in ABAQUS. Try and open that file. So the ODB file, which is the first case that we've run, and then look at the result. Okay, some interesting values that we're getting. So we can exaggerate that a bit by making maybe this to become 1.5. So we get a significant deformation. So this basically tells you, so especially if you compare the two together. So what we are looking at here is a deformation where you have a shear loading due to this pulling in this up direction and pulling in that direction, as well as the tensile loading, because this front end is being pulled. So you end up with the front end being pulled, and also you get the classic shear deformation, which is this kind of angular behavior. So that tells you that this is really a combined loading scenario, and we've got our result for that. So what of the second case? So again, we navigate back to the negative case, look at the result. Now in this case it's different because it's no more pulling out. So what you could see is that the front end is being pushed. So if we animate that, so you could see it starts up and you're pulling in the front end to create this compressive loading, as well as the normal shear load that you're generating as well. So clearly those two simulations are different. One is a tensile pull, the other one is a compressive pull. And hopefully we can go ahead and visualize the stress strain data from this. So what we're going to do is look at the positive case, the first positive case. How do we extract stress strain data for that? Now what I'm going to do here is I'll click on this create XY data. We already have a history output associated with this because we told the simulation to generate that, and those were the coordinate nodes. So I'll press down shift, select those, and then go to here, press down control and drag until you select all that. So what we are selecting here are the displacement data, the reaction forces, and the coordinate positions. So we plot them. Now what you're already beginning to see is that there are two sets of curves, one being maybe for the uniaxial case, the other one for the shear case in this first instance. And then of course another jumble of data points. But what will really be interesting is for us to play with these values. So plugins, tools, Excel utility. So what I'm trying to do is to take this current plot and export it into Excel so that I can get the raw data that I can begin to manipulate on them. Again, the video in the link is where I showed how you can generate stress strain data for a PBC enabled domain. That will be really useful if you want to learn a bit more about this. So what we have here is the actual data. So I'll just copy. So I'll copy all that, which is the raw data that we have. So now what we are going to do is I've prepared a spreadsheet, and in that spreadsheet, we can then go and copy and paste the data from the uniaxial case instance that we have, which is this. That's the uniaxial state case to the end. The other thing you need to note is that the length of the RV is 120, the width is 120, because it's a 1D problem, the thickness is 1. So we can then, again, just look at that video that I've made about this to show you how you can understand what is happening here. So at the end, we generate some force data, some strain data, and some stress data. And then we plot them together to generate this graph. Okay, so with the same data, nothing changed. Exactly the same data that you've used to generate this uniaxial case. You use the same data, exactly the same data, paste it in the same environment. The implementation here is slightly different in terms of generating your force. So again, please do check the script to see the slight difference in terms of generating your shear. So we are using the same nodal values to determine what will happen in the x direction and what will in the uniaxial direction and what will happen in the shear direction. This is really neat. This is really very exciting to be able to do this. So you use the same data that's taken from the simulation you've run, and you're plotting the stress trace as well as the uniaxial stress as well as the shear stress trace. And when you plot them and then I put them all together, then you could see what's happening, the result. So now we finished running and setting up the model and generated the stress strain data. And this is the stress strain data. And you can see in the stress strain data, there's a combination of a uniaxial deformation in green and a pure shear deformation in red. And we extracted the values from those. If you think about the values, so what we're looking at here basically is this value for the strength of in the shear direction, and also the other value for the strength in the x direction. So we'll combine those two together. Now, how do we reflect this in terms of our graph? So again, if we go back to the expected failure envelope. So this is sort of the failure envelope. So what we are really looking at is this particular simulation can be a point on that data at this point. Okay, so because we take a value in the x direction and a value in the y direction, so a combination of those two loading will create a point on the stress strain data. So if we look in this case, on the x-axis it's about 26.2 megapascal, on the y-axis 27.5 megapascal. So this is the value you get from an interaction of a certain value of uniaxial x loading in the X direction with a shear which is loading in the Y direction. And this interaction will lead to a premature failure of just around 27, 26, 27 megapascal. So you could imagine as you keep combining those two, you could then keep going all the way around until you combine and generate all the failure for this failure envelope. So this is how we're going to go about this. And hopefully at this point, we have given some insights to Ella as she tries to explore her problem of how can I generate failure envelope for a composite material that the supervisor tags that with. If this is the kind of content that you like, please do subscribe to this channel and click the bell button so that when contents like this are made, you'll be the first to see it. Thank you very much and catch you in the next video. Bye-bye.